Okay. Bonjour, bienvenue. Would people prefer if I present in French? No? Okay. I was told to at least ask. Wonderful. Well, thanks for joining me today. I know it's tough to break away from the cookies down on the ground floor. Okay, so today we're going to be talking about OpenStack on ARM. We're going to talk a little bit about this project, what it's all about, what ARM is all about, the processor. We're going to talk a little bit about the installer that we used to install OpenStack and our build methodology. So we use Terraform, so we'll get into some of the details about that. We're going to talk about the fixes that we had to do to get OpenStack to work on top of ARM and the changes and modifications. We're going to talk a little about the hardware configurations, where we used some ARM processors and systems from a couple of different vendors. So we're going to talk about those different configurations. A little bit about the testing that we did, the performance testing we did on top of these different ARM systems, and the methodology, and then the results, and then where we're taking this work from there. Okay, so a little bit about me. So I do freelance OpenStack and security product advising. I'm also one of the OpenStack ambassadors in the US, so that means I help organize presentations and meet up user groups across the US. So if you have some interest in that, happy to talk to you about that. I've got one other presentation at the summit today, Wednesday afternoon, I think it's at 1 o'clock or so, on the Passport program. We went and we spun up the Passport program. This is the public OpenStack cloud, and gave that a whirl, and our results from that. A couple of other past projects. First of all, this project is fully up on GitHub. So it's that first URL there, github.com, works on ARM. OpenStack works on ARM. So everything that you see today, all of the installer, all the Terraform, everything you need, it's all up there. You're welcome to clone it. You're welcome to submit fixes or whatever. And then a couple of others, security service change. That's a workshop I did at previous summits. It's how to use service function chaining within OpenStack to implement security rules within the software-defined networking. And then a couple of other workshops that we've done in the past, a Magnum, and then a cloud storage workshop that we've given at past summits. So you're welcome to take a look at those. And if you want to try out one of the workshops, everything you need is right there on GitHub to give it a try. Okay, so a little bit about this project. Packet Host, I approached them about a year ago. They are a bare metal service provider, and I asked them if they would be kind enough to donate resources that we could use to build some OpenStack clouds to run in our user meetup groups. So that's how the relationship started then. Packet is actually partially owned by SoftBank, which is a big ARM processor vendor, financing. And so Packet approached me and said, hey, we've got these ARM systems. We'd like to see people start using them for different projects. Can we see if we can use them for OpenStack? And that's how the relationship started there. So we decided to say, hey, can we take the default OpenStack installer that you just find on openstack.org? Can we take it and can we run it? We want it to be totally vendor agnostic, totally vendor neutral. Can we run it? Will it work on ARM? Will it work well on ARM? Does it make sense? Are there any showstoppers? Are there any fixes we have to do? So, and does it make sense from a financial perspective? Does the price point that Packet sell these systems at, they rent systems out by the hour, as compared to an x86, make sense to run OpenStack on those systems? And a couple other things. Can we mix together an x86 and a ARM system, cloud together with a bunch of different systems? And then most of all, make it all available, submit the fixes that are required to get it all work back upstream, so it's all patched in, and hopefully people can find it useful. And they have. We've gotten a couple of people using it for some CI/CD work. So first of all, ARM. What is ARM? What's it all about? It's a new type of processor. It was originally designed for use on mobile, low-power devices, so in your cell phones. Since then, it started being built into servers, higher performance, and higher performance in the ARM point of view means more cores as opposed to faster processors. So you'll see ARM systems that contain a lot of cores inside of it. We'll see some that's got like 96 cores on it. And in the x86 world, things scale up by you get faster and faster processors. In the ARM world, you're going to see them scale out instead by having more and more cores. So we want to take a look. Can we use that in OpenStack? Can we use this ability of scaling out through more cores? And there are a bunch of different processors, different systems. So in this test, we went through a couple of different models. So Cloudflare. Cloudflare is a CDN, content distribution network. They're probably one of the largest ones out there. And they went through and they replaced their x86 workloads, their network across the world, various data centers, replaced them with ARM servers. And the feedback from the CEO is the cost savings for using ARM systems more than paid off for the expense. And even if Intel gave them the x86 systems for free, it still made more sense to pay for the ARM systems based upon the operational costs that they're saving. So the question is, hey, it worked for Cloudflare. Can we make the same thing work on the OpenStack side? So why Packet? Why use systems from Packet? So for me, building out these lab environments, installing OpenStack, especially from bare metal, takes time. You got to go through, get all the hardware, plug it all together, make sure the hardware works, network correctly, operating system installed. So what Packet has is basically APIs you can hook into, call the APIs, get the hardware provisioned for you, and the operating system installed in a fully replicated manner in a matter of minutes. So 5, 6, 7 minutes, I can get a cluster of multiple machines up and ready to go, and the hooks tie into provisioning tools such as Terraform. They had a combination of both x86 and ARM systems, so I could replicate the same Terraform runs across the different types of servers. And so it allowed me to basically ramp up, set up these clouds, half an hour, I can get a new cloud, 15, 20 minutes, get a new cloud going, multiple compute nodes, multiple controller nodes inside the cloud, run my test, tear it all down very quickly, and I could repeat the same things across the different types, and I could even repeat the same tests on the same hardware if I needed to go through and have make everything happen repeatably. Okay, so let's run through a little bit about the different hardware that Packet made available. The far left there, we see the different code names. This is sort of the internal name that Packet uses. So T0, T1, the C2 medium, the processor family, the thermal displacement. So basically, this is how much power and energy the machine kicks off. I think when you take a look at power usage, keep in mind, not only is it the power that the system uses to run, but it's also the amount of heat that it generates. So systems that generate heats, it multiplies into the fact that you need air conditioning to keep it cooled down. So you got a double-edged sword there, that you're getting hit on both more power and power needed to cool it. So if you take a look at the last three, those are the ARM systems. You can see that there are quite a few more cores there. That KVM ThunderX has got 96 cores, the Huawei 64, and the Qualcomm 40 cores. So quite a few more cores there, we'll see. All of them had SSD drives, so pretty similar there. All of the high-end ones had dual 10 gigabit network cards installed. Okay, so what did we do to go through build each of these clouds to run these performance tests? So we got a repo in there up in GitHub. It's got all the Terraform, everything you need to go through and configure it. So we added variables. For those who are familiar with Terraform, it's vars.tf. That goes through, it has all the variables that we set, the number of control nodes we want, number of compute nodes we want, the type of control nodes, the processor type, the system type, going back to that Packet list of systems. So we define all of that. Install Terraform if you don't have it on your system. Pull in the plugins. The plugins are what are use the glue between Terraform. So Terraform and the Packet APIs, the command Terraform init will set all that up. We need a couple of tokens. Those are the API tokens to authenticate yourself to your Packet account. We need to set up some SSH keys, and then we execute Terraform, wait about 10, 15, 20 minutes for the cloud to build, and the output of the Terraform is basically the credentials you need to log into your OpenStack cloud. So the SSH to SSH into the controller, and also the URL to log into Horizon. So that's it at a quick glance. We're going to dive into the specific details underneath. Okay, so our installer, it has the ability to do a combination of ARM and x86, any number of instances that you want to do. Fast installation. Terraform is very smart to figuring out how to run everything in parallel. So you have, if you want to spin up 5 machines, it'll spin up all 5 machines in parallel, and it can keep track of where everything is and what the next steps are. So it allows things to spin up very quickly. The installer steps that we took, we basically, everything you need to do Pike that's up on docs.openstack.org, we took those steps, put them into Terraform Installer. Basically, if you are just going through from scratch, following all the instructions by hand, as opposed to using one of the vendor installs. And then we had 3 different types of nodes that we set up within Terraform. A controller node, that's the brains of an OpenStack cloud. The compute node, which is the muscle where all the hypervisors run. And then a dashboard, which is basically the human interface to the horizon. OK, so let's take a look at the provider, the bare metal provider. This is the glue code between Terraform and the Packet APIs. So there are a couple of environment variables that we set, the tokens, and then the project IDs. So if you're familiar with AWS, it's the same sort of idea, basically where we're going to deploy everything into. And then we go through and we set that up in the configuration file or as environment variables. So ideally, you set them up as environment variables. You don't want to have these sort of credentials baked into your code. OK, and then also in the Terraform vars file, we go through and we say the number and the type of each of the controllers. So here you can see that first one, packet controller type. So that is the bare metal type of the controller that we're building. In this case, it's a bare metal 2A. And if you look back at the notes, a 2A is one of the ARM-based systems. And the dashboard is a bare metal 2A as well. Once again, it's one of the ARM systems. The compute x86 compute is bare metal 0. That's one of the Atom systems. And then the compute x86 count is the number of compute nodes we want to build out in this cloud. So in this case, we set it to 1. But you basically configure that to how big and the type of bare metal that you want. So in this test, we ran a bunch of different clouds, different configurations. We ran some clouds that were all identical components, so all exactly the same type of ARM system or all exactly the same type of x86 system. We also built out clouds that were a combination of ARM and 86. In total, we built out 7 different clouds and ran performance tests and functional tests to make sure they work properly. And then we also ran some of them concurrently. So even though they were completely separate clouds, we ran at the same time just to take a look at what would happen. And one of the things we noticed is when you're running multiple clouds, you have multiple physical nodes, and you don't know which one they belong to. So we introduced something into Terraform where we go and we tag the physical hosts. Packet has the ability to add metadata on to each physical compute node. So within Terraform, we create this cloud ID, which is that 4-byte length random number that gets created, and then we tag it to each physical node. So then when you pull up the Packet user interface, you will see a tag column that has an OpenStack cloud ID. So you can associate which physical machines belong to what OpenStack cloud. So sort of a neat little trick we did there. OK, and a little bit about the environments that we ran it. We ran all of these tests in the same Packet data center. Packet has multiple data centers you can deploy across all of them. Just to keep all the tests consistent, we ran them all in the Newark data center. We didn't use any type of DNS. Instead, we had Terraform configure a host file, and we put all the host entries in there to reduce any type of external dependencies. And then we uploaded a bunch of VM images that we had available across both x86 and ARM. OK, so as we talked about, we went through, we defined. This is just clicks to go through, and you can actually see those settings in the GitHub. So when we run Terraform, here you can see just a dependency graph that gives you a little feel of what happens when you run Terraform. So the first 6 minutes and 50 seconds is the bare metal systems being provisioned, the operating systems being installed on all of them, the host files being generated across all of the IPs that are assigned to these systems, and then the host files being distributed back out to all the machines. So at the end of 6 minutes and 50 seconds, bingo, we've got however many physical machines you needed across your compute and control nodes. And then Terraform steps the next step down, which is actually installing the OpenStack software. So here on the left, you can see 4 minutes and 30 seconds it takes for the controller to get set up, about 1 minute and 50 seconds for a compute node for that software to be installed. And those happen in parallel. Once the controller node is set up, the next dependencies are pulling in the images. Those get pulled in once Glance is up and running. And in total, it takes about 5 minutes and 30 seconds in this install for the full OpenStack to be up and running with the controller nodes and all the compute nodes. So pretty quick, you know, so that's 7 minutes plus another 5.5 minutes, 6 minutes. So 13 minutes, we're up at the point where all the APIs are running, where the dashboard's running. And then the last step is setting up all of basically the virtual workloads. So setting up all the virtual networking, setting up any floating IPs, spinning up the virtual machines that make up the tests that we're running. So, and that in total was 1 minute and 10 seconds. So you can see, basically we can go through and we can spin these machines up pretty quickly. So the output of Terraform, once this is all done, this is what you end up seeing. It'll give you a list of what all the ARM compute IPs are. So in this case, we have one of them. Tells us the physical bare metal type. So in this type, it's bare metal 2A. A list of all the IP addresses of the x86 compute nodes, what type they are. It'll give you the command to SSH into the controller node, and then it'll also give you the URL to connect into the Horizon dashboard. So that's the output, final output, so to log into the cloud. Okay, so let's talk a little bit about what we had to do to the stock installer that's available on openstack.org to get it to work. First patch, and you can click on these, and it'll take you directly into GitHub, and you can see the actual changes. I took snapshots, as many as I could. First thing is, etcd, the install instructions are hard-coded for x86, so this is a pretty easy fix that we had to do. Basically went through and just checked the architecture type, and if it's x86, we pulled in the x86 binaries. If it's an ARM system, we pulled in the ARM etcd. Interesting enough, the etcd for ARM64 is deemed experimental, so you need to do a couple of extra flags just to mark down that you accept that it's experimental. So on the right there, you can see environment equals etcd, unsupported architecture equals ARM64. So a couple of small changes there. We need some extra firmware and KVM configurations on the compute nodes. So small little change there. Sort of a larger one, the ARM systems do not support VNC. So you need to turn that off in the compute nodes and instead use a client program called Nova Console, which will connect into the serial port and get you the output there. So we're turning off VNC in the compute nodes, and we're installing some extra software called Nova Console, which unfortunately means that the console within Horizon does not work for the ARM64 systems, and you have to use this command line to get to the consoles. And of course, we pulled in some ARM VM images. So we just, across the internet, found as many as we could. So actually, we found Cirrus, Fedora, a couple of different Ubuntus, CentOS. Not all of them currently work. Some of them, you get stuck in a boot prompt, but we'd had enough that we're able to get through and run these. So, and you also have to set, if you can see there, property. You have to let it know that the firmware type to make sure those images boot correctly. Okay, so we've got our cloud running, we've got the patches in place. So let's do some functional testing. So we want to check, do x86 and ARM64 VM startup okay? Do all the services run correctly when the controller nodes are ARM64? Can ARM and x86 workloads talk to each other over the TCP/IP network? So first thing, validation. Let's take a look at all the services that are running, and here we can see, yep, we've got all the services running. They're working correctly across a ARM64. Can we see all the cores running okay? So in this case, we got a 96 core machine. So we go through and we say, okay, give us the hypervisor output, hypervisor information for this compute node. And we can see all the memory, we can see all the compute nodes. I mean, it's not compute nodes. We can see all the CPUs, all the cores. And let's go through and spin up a combination of ARM and x86 workloads. So here we got a combination of Fedora, CentOS, and Cirrus running. Networking works between them. The scheduler is smart enough to know that the ARM systems need to run on ARM compute nodes, and the x86 needs to run on x86 nodes. If you try and spin up an x86 VM and you only have ARM64 compute nodes, it's not going to spin up, right? You don't have the right processor type available. So the scheduler works just fine there, no issues, which is great to see. Okay, so let's run through performance testing. So now we got these things running. Let's find out what sort of performance numbers do we get out of it. We're going to do some 95th percentile. We're going to do some keystone add and delete users. We're going to do some typical virtual machine spin-ups. We are going to run these through 1,000 times, 10 queries concurrently. We're looking for a zero error rate, and we want to make sure it passes the Rally minimum service level. And so basically we went through, set up Rally. For people who aren't familiar, Rally is a OpenStack testing tool. It goes through and it hits all the APIs for you, gives you some nice XML output, which you can go through and then build out some HTML pages. So installed Rally, went through, ran Rally against all of the different clouds that we built out to get us our 95th percentile numbers. Okay, so let's take a look at the results here. We've got all of our different families there of processors. We've got that thermal displacement, so how much power they're using. And then we've got that cost dollar per hour. So what that dollar per hour is actually the packet retail price, what packet charges per hour to run each of those systems. So you get to use some sort of real world capitalistic value that is supposed to include everything from CapEx cost of buying the hardware as well as the operational cost for running it. That's what they charge customers per hour to use. Account management, this is that keystone activity of setting up a user account and tearing it down through Rally. And then the VM management is going through spinning up a VM and then tearing down that virtual machine. So the first two AMD machines, we fail on the VM management. Unfortunately, a network that consists of those two machines isn't able to handle 10 concurrent requests. So it can handle it on the user management side, but it can't handle additional workload. So in that case, we went ahead and we failed those. We said, okay, they didn't pass the minimum acceptable level. But the next one did, that AMD EPYC system did, and you can see 2 seconds to go through and run through the account management tests on average. That's a 95th percentile, 15.9 seconds on the VM management. So go ahead and spin up that 10 of them. Then the next thing through, the KVM, the Huawei, the Qualcomm, we can sort of see, if we get all the way down to the Qualcomm, okay, we're at 24.5 seconds as compared to the AMD at 15 seconds. We see, okay, the price point, they're both $1 retail, but the Qualcomm is using 110 watts of power versus the AMD using 155. So, there's a power cost ratio, and you figure maybe twice as much cost to run something that's using 50% more power between the two. So you start to get some feel, okay, maybe they start matching up there. But interesting enough, these performance tests are not stressed out to find out what's the maximum that these can hit, right? What we're doing is making sure we can get some minimum baseline performance out of 10 concurrent requests out of this. Or will the user get some acceptable results out of using it, or is it going to feel too slow and sluggish? That's what we're really concerned about. Okay, so our results. Is OpenStack ready for ARM? Yes, it works. Functionally, we got everything working. There are some tweaks that have to be done to the installer, to the stock. A bunch of different vendors they've got their version of OpenStack running on ARM. We wanted to make sure, the full upstream, does it work? Or can we make it work? And yes, we can make it work. Does it make sense to run OpenStack on ARM? Well, you got a couple of things to factor. Are your workloads, can they run on ARM? You got to go back to your companies and you got to go back to your developers and say, can you guys recompile this on ARM? Does it make sense from a perspective to your business applications to work on ARM? Let's take a look at the controllers, though. The controllers are running OpenStack code. So that code works on there, and that's independent of your business workloads. So maybe you can go and run your controller nodes on ARM and then take your old x86 controller nodes and use those to build out your compute nodes instead and move around your hardware that way. Can we mix ARM and x86 together? Yep, you can definitely mix them together. And it goes back to this, maybe you go and you run your controller nodes, maybe you run your storage nodes on ARM, and then you can save the x86 ones for your business applications. So since then, we've gone through, done some additional work. We've pulled in some additional virtual machine images, got them going. We've added in external networking. Packet has the ability to dynamically request through the APIs external publicly accessible IP addresses, so you can add additional floating. You can add them in as floating networks, floating IPs into as a public network into your OpenStack cloud. So we've added in support for that. We've had one open source project start using it for as a CI/CD environment for them to start testing out and building out their applications or their libraries on top of ARM system as well. And where do we want to go from here? So we want to build out the installer, the Terraform installer, so we can scale up and scale down the bare metal. So right now it's sort of static. You can't scale it down because it's not going to migrate VMs off, so add things like that. Definitely want to do more on the stress testing side, find out, can we really scale out? We've got this bunch of ARM processors, lots of cores. Can we scale out? Can we run as, can we get a larger number of concurrent requests going through the ARM systems than we can get working on the x86? And there are a couple of minor glitches here. Console logging doesn't go through. We can't pull up the console within Horizon. Can we see about getting some of those things fixed? So don't be shy. If you got any questions, I'll be interested to hear. I have one more slide while you guys think about any questions you might have. So most of all, looking for people to get involved. Like I said, this is a fun little project. We've got, if you're interested in giving this a try, I've got some code so you can get some free computing resources from Packet. They'll give you $25. That's more than enough to go through and spin this up if you want to give it a shot. Spin up a couple of ARM or x86 systems. So see about this. If you're a developer and you've got something that maybe runs on x86, you want to give it a try on ARM, let me know. We can get you some resources on ARM, either in an OpenStack cloud or standalone from that. And thanks everyone for showing up. Okay, we got one question. Okay, so your question is, what would be needed? I'm just repeating it for the microphone. What would be needed to extend this installer for the Ansible installer, or a vendor neutral? Okay, so I did try the Ansible installer from the beginning because I felt, hey, that is a vendor neutral one, like you said. The first thing I ran into with Ansible is using Linux containers, and that was sort of a larger roadblock than I was willing to tackle at the beginning. But I think that's the first thing that needs to get figured out. Would it make sense to use an Ansible installer? Definitely. I mean, I think that's one of the biggest installers out there. And part of the reason I went down this route is because I wanted to use just those pure installer instructions on OpenStack. But I think it definitely would make sense to go through and take some of these changes, incorporate them in, get the Linux container component working on ARM. I have a feeling it's probably the same thing that etcd was doing, where it's probably hard-coded in to do x86 instead of checking the architecture type on the system, if I were to place a bet on something. But yeah, definitely a way to go. Are you involved on that project? Not directly, okay. Any other questions? Okay.
What about Open vSwitch?
So what about Open vSwitch? So we used, this used Linux bridges. So that's what the installer, or that's what the default OpenStack. Off the top of my head, I can't think of anything that would prevent it, but no, I didn't. I didn't try that one in particular. Is it worth trying? Sure.
I would need it to work with
Okay. Okay. So I can put that down as one of the nice to add on, or nice thing to put on the list of things to try out. Okay. Yep.
Do you have any theories as to why the KVM node was so much slower?
Any ideas on why the KVM node was so much slower? Is there anyone from KVM here? Is there anyone from any ARM?
Yes, because they didn't release version 2 yet.
Yeah, okay, so one response was they didn't release version 2 yet. Yeah, the KVM one is definitely the ARM system that has been out the longest. The Qualcomm one, at the time we did this, was like bleeding edge, definitely ahead of the pack. Yeah, I think it's just, it's an early prototype, or not a prototype, but it's just one of the Gen 1
They don't
systems.
Parallelization and construction.
Okay. So, like I said, first generation of the system. So, that's yes. Why is VNC not supported in ARM? My understanding is it's because there's no what's the right term? Was it display buffer? It doesn't have the not. I'll look it up offline and get the answer to you. It just doesn't have the same display that's available out in the x86. So I'll look it up. I'll get you the detail on it. Yeah.
Are there any specific workloads that can get most profit from running on ARM VM as versus
The x86. Yeah. So are there any workloads? Are there any OpenStack workloads? Is that specifically?
not
Yeah.
necessarily. I mean workloads running in a VM.
Right. So what workloads would make sense to run on an ARM system? I know one use case is for Ceph, the idea that you could have multiple spindles, multiple storage devices, and that parallelizes well across multiple cores. So I think anything that you can parallelize, is it running containers, multiple containers across multiple cores, so you get a one-to-one matching in that regard. On the OpenStack side, I think definitely on the storage side, you'll see, from what I understand, is a lot of vendors are coming out with boxes with a lot of spindles inside of it to coincide with all of the cores. So things like Ceph. Yes?
What was the failure mode that we saw on the x86 systems?
Right. So what's the failure mode on the lower end x86 systems? So basically, the API would get overloaded, and Rally would make requests, and then the API just wouldn't respond back. So first, it would just slow down, and then basically it would stop responding to it.
So we hit Rally's internal timeout.
Say that again?
So was it when it was hitting Rally's internal timeout, or when the request actually failed?
I'm pretty sure in there, I put a timeout. There is a timeout on there. I want to say it's 3 seconds. Yes, there is a timeout value in Rally. So basically, that's the SLA. If it doesn't respond back within that, then that's considered a failure. It's not performing at a minimum level. Anyone else?
Probably for your Docker one, they have to actually build the Docker images with the ARM. That's one of our use cases, actually. One of our products is, well, a couple of our products is ARM-based.
Mm-hmm.
And you have to use ARM to build the Docker images in ARM.
Ah, okay.
I think there's a way of tagging images as multiple targets, but it's all complicated.
So which images are you talking about?
The Docker image,
The-
the thing that's used to instantiate the containers.
Oh, are you going back to the Ansible installer? Is that what you're talking about?
Maybe.
Okay.
I'm answering the Docker.
If Docker's a good use case for it? Okay.
So, sorry to interrupt. For the Docker images, all you need is an image manifest file. The problem is that Docker Hub doesn't support anything but x86 today. We're working to change that. The official images do support, so if you have an official image, we're expanding those. But as far as creating multiple binaries, specifying an image, which is it's JSON YAML, it's very easy to do. The problem is building it and finding ARM hardware or a VM in the public is a little bit difficult. So you understand.
Okay. Well, if that's it, thanks again.